Okay, so we have our third lesson on the extended practical investigation, and this one's just going to be a whole slather of concepts related to just doing experiments. So just before I forget to mention, what's going to be happening is that you'll be starting on the extended practical investigation. I'm recording this on the, what day is it today, Jesus? Wednesday of week 6, and we'll be starting that hopefully in the Monday of week 8. So as I'm recording this, there's still some uncertainty. Why am I telling you this? Just so that you know when you'll be starting on the experiment, and the fact that if you're watching this video, I'm still a bit uncertain about what form it's going to take. I've got a plan, but at the same time I've got to talk with the teacher at NERM. So got a bit of time for me to do that, although even though when you watch the video it won't seem like that. So first of all, we're going to cover something that's hopefully everyone's seen a whole bunch of times. You would have seen it across all your science subjects, and that has to do with variables. So when someone does an experiment, they alter one variable, and they see the impact of this by measuring a different variable, which is the outcome of the experiment. So we've got our independent, dependent, and controlled variables. Normally you see the independent and dependent ones quite a bit, and the controlled ones pop up. I like to include them in my junior science classes, but maybe you haven't seen them as much. So independent is the one which is altered directly by the experimenter, and a dependent one is what you measure as the outcome of the experiment. Now, controlled variables require you to have a decent understanding of what's going on in the experiment. It's something that needs to be kept constant for the experiment to be valid. You don't want to go changing things that you don't want to change, otherwise that can impact on your results in ways that are going to mislead you about what your results are saying. So to go through an example, I want to see how changing the temperature of a bowl affects its bounce height. My heater's on, so if that's coming through in the video, the sound of that, I apologize. And it's asking if I'm changing the temperature of a bowl to see how that affects its bounce height. I get a tennis ball, I put it in some hot water, or I heat it up without getting it wet somehow, or I put in some ice water and cool it down, and I see how changing the temperature affects its bounce height. So the question is, what are the independent, dependent, and controlled variables that are involved? Well, the thing that I'm altering is the temperature of the bowl. I want to see how changing that affects my bounce height. So the thing that I control and affect is the temperature of the bowl. That's my independent variable. What I measure is how high it bounces up. So I want to keep, that's what I'm going to measure. That's going to be my dependent variable. It depends on my changes to the experiment. So that's a handy way of remembering it. The dependent one depends on the changes that you make. And the third one is I would need to drop it from the same height each time in order to be able to compare the bounce heights reliably. If I'm dropping it from a meter above the ground and measuring the bounce height at one temperature, if I change my temperature and now I'm dropping it from 2 meters, I can't really say much about how the temperature has affected my bounce height because I've changed a different variable, and by changing that, it's going to affect my results as well as the change in temperature. Another thing might be whether the bowl's wet or not. You'd want to keep that the same throughout your measurements, so that the effect of having the bowl be wet in one experiment isn't going to be impacting on your comparisons between different bounce heights. So that's just what a controlled variable is. It's something that remains constant throughout your experiments, and I think bounce height's a good illustration. Not bounce height, drop height that you drop the ball from is a good illustration of that. Now, moving on to a different experiment concept, and that is on significant figures. Now, significant figures have always been a bit of a controversial thing in physics. When you do an exam, you don't really have to care about significant figures. So if you get out an answer, you don't have to stop and go, hey, does it have the correct number of significant figures in physics? Because questions, as far as I know, don't get assessed that way. I've heard murmurings that might have changed, but I don't think that's the case. So as yet, it's different in things like chemistry. In chemistry, the way they do it is that every year there is like one question on the exam, and for the whole exam in chemistry, you're expected to get, why am I talking about chemistry? You're expected to get the right significant figures for every question, but there's one question that they look at and they go, did you get the right significant figures for this one question? And if you did not, you lose a mark, and if you didn't do it for your other questions, it doesn't matter. But in physics, it doesn't matter, except if the question is specifically how many significant figures does this have, or make it have 3 significant figures or something like that. So unless it specifically says significant figures in physics, as far as I know, this was the case like a couple of years ago, and I haven't heard anything about changing these. We just don't need to get it to answers to the right significant figures, but questions about them might still pop up. So significant figures, it's basically if you have your number in scientific notation, how many digits is it going to have? So my first example is going to be 342.5. I turn that to scientific notation, 3.425 times 10 to the power of 2. That's got 4 digits, so it's got 4 significant figures. My second example is 0.0023. In scientific notation, it's 2.3 times 10 to the minus 3. That's got 2 digits. It's got 2 significant figures. Third one is 0.203. In scientific notation, 2.03 times 10 to the negative 2. That's got 3 digits. It's got 3 significant figures. So that's just how this is going to work. The next one's going to be, I probably should have included an example like the next one, but whatever. You get the gist of it. So when we're dealing with significant figures, we also think about doing calculations with them. So the first dot point's a bit of a mouthful, but it makes sense once you get the gist of it. When we calculate quantities based off other quantities that we already know, our answer should have the same number of significant figures as the starting quantity with the least number of significant figures. So there's a lot there. So my example is I'm doing a distance equals speed times time calculation. That's about as basic as physics gets. So if the speed was 5 meters per second and the time was 3.5822 seconds, what distance would be traveled? Well, to find the actual distance with calculation, I do distance equals speed 5 times time 3.5822. That gets me out 17.911 meters per second. Now, this answer has 5 significant figures, so those 5 digits there. 5 meters per second has 1 significant figure. 3.5822, my time, had 5 significant figures. So to repeat what I said earlier, the answer should have the same number of significant figures as the starting quantity with the least number of significant figures. So 5 meters per second had 1, 3.5822 had 5. So my answer should only have 1 significant figure, the same amount as the starting quantity with the least amount of significant figures, just 1 significant figure. So that means I've got to write my answer. Some people might be tempted to write 18 meters per second, rounded to the nearest meter per second, but 18, that's 1.8 times 2. It's 1.8 times 10 to the power of 1 meters per second. That's 2 significant figures. So to make it into only having 1 significant figure, I'd have to round it up to 20 meters per second, kind of. So that 20 could be written as 2 times 10 to the power of 1 meters per second. It's just got 1 digit. It's got 1 significant figure, which is how many we want. So I'd be rounding my answer quite a bit from 17.911 up to 20, just to make sure that my answer has 1 significant figure. But please don't do that for just random questions unless it says make them have the right number of significant figures, which I don't think there's ever been a physics question that looks like that, but it's technically part of the study design, so it could be on the exam. That's why I'm bringing it up. But yeah, if you round your answers like that, the way I've done, you're at risk of actually losing marks because you're rounding them so severely. And if they expect the answer to be like 17.9 then, and you write 20, they might just say that it's wrong. So yeah, just keep that in mind. Significant figures are kind of an iffy subject. And I guess that kind of raises the question of if you're doing an exam, how many decimals should you be writing? How detailed should you get if it doesn't tell you? Normally I just say, look, if this one it was 17.911, I just normally write that, or 17.91. Normally if I have a bit of leeway about how many decimals I go down to like 2 decimals. That's like my rule, but it's not a universal rule, and it's, like I said, not that important. It's about showing your understanding of the physics. That's the main concern. So don't worry too much about significant figures in terms of just you get an answer, you don't need to round it to the correct number. But I'm just bringing this up because it's part of the study design, and there might be a question that says make this have the right number of significant figures. So just something to keep in the back of your head. Now, I think this is the last one. One of the other things that we look at regarding physics experiments are the difference between a model and a theory and a hypothesis. So a hypothesis is probably the one that you've probably used the most in science. You use the words model and theory all the time, of course, in science, but hypothesis, every time you normally write up a science report, you start out with a hypothesis about what you thought would happen, and so it's probably the most commonplace one. And I just Googled the definition of hypothesis. I wanted a good definition, and then Google provided. So it's a proposed explanation made on the basis of limited evidence as a starting point for further investigation. That's a really nice definition. It says that you've got some reason for thinking things are going to go the way they do. You've got some idea that things are going to go a certain way on the basis of some limited evidence, and when you do your experiment, you're going to be doing a further investigation that sort of extends what you know into the realm of what you don't know. So you've got a basic idea in your head already, and you just basically use that to think about what's going to happen when you do a further investigation. So good definition of hypothesis, really like that. A model, by contrast, is a way of explaining things that works within a limited context. So we looked at Bohr's model of the atom in our previous area of study, which was about electron energy levels in atoms and all that, and we said that it works really well for hydrogen atoms, and it works really well for hydrogen-like atoms with only one electron orbiting them. So evidence shows that that model isn't correct for all atoms. Things work more complicated in more complicated ways for atoms with more than one electron, but the model still works for particular atoms. It's got its context. It's not a universal way that applies to everything. It's only got specific scenarios in which it's going to hold. So that's what it is to be a model in physics. It is that it's a way of explaining things, and it's not going to work every time. It's a simplified version of reality, but within certain contexts, it's going to work, it's going to do its job. So the last thing that we do, that we contrast hypothesis and model with, is a theory, which is basically our hypothesis that's been confirmed through repeated experiments. You've got evidence that supports your hypothesis, is really the gist of a theory, and you've done it through a few different experiments, different sources of data kind of supporting your hypothesis. That's what a theory in physics amounts to. It's not just I've got an idea. It's actually a pretty specific definition in physics and science in general, that a theory is something that's got evidence backing it up. If there's no evidence really backing it up, in science it doesn't really constitute a theory. That evidence needs to be there. So I think that's essentially it for this PowerPoint. Like I said, I think I've basically covered all the background content that you need to know. Like I said, all this stuff is examinable, and there's a lot of examinable stuff. Like every year now, there's a fair bit of stuff on this on the exam, and it's just kind of scattershot about exactly which concepts make it onto the exam each year and which ones don't. So all this stuff you're going to need to know for the exam. I can't say that you don't need to know this or you don't need to know that, because well, in previous years they only pull certain concepts, and maybe they'll pull one this year for the exam that they haven't used before. Safe to just make sure you're on top of all this stuff rather than hoping it's just not on the exam. So I think this is my last PowerPoint of theory related to the extended practical investigation. We're going to have a think. I'm going to have a think and a talk with the NIRM teacher about how we carry it out, just to make sure that everything's going to be good. I've got a few different ideas about how to do it, and it's just about narrowing it down to one of those. So you should just be working on your checkpoints questions, and there are some Ed Rollo questions as well. I don't think I can, like the way I've put these PowerPoints together, I can't really go, okay, you've watched this video from me, now watch these Ed Rollo videos and answer these quiz questions the way we've been doing. You might just want to take a bit of time and actually watch through those Ed Rollo videos, because I think they cover a few different things about setting up the experiment, maybe not what I've talked about, but I'm rambling at this point. They're still valuable. So yeah, that is essentially it from me today.